Hello there. I'm glad you're here tonight. As you settle in, let your breathing slow and your thoughts soften. If these calm science journeys help you rest, you're welcome to subscribe so they can find you again. And if you're still awake, tell me where you're listening from. It's always comforting to know. Now let your mind grow quiet as we begin with a star on the edge of its final transformation. You begin by imagining a massive star in the quiet stage just before its life changes forever. For millions of years, it holds itself steady through a balanced exchange of forces. Nuclear fusion at its core produces heat and radiation that push outward, while gravity tries to pull everything inward. This balance, called hydrostatic equilibrium, keeps the star stable. You follow this balance gently, feeling how it depends entirely on the star's ability to fuse lighter elements into heavier ones. As long as fuel remains, the outward pressure continues to counter gravity's inward pull. But eventually, you notice that the fusion reactions slow. The innermost layers of the star begin to run out of usable fuel. Hydrogen is long gone, replaced by helium, carbon, oxygen, and heavier nuclei that formed through earlier stages of fusion. As the available energy supply diminishes, the outward pressure weakens. Gravity, always present, begins to dominate. You sense the beginning of an irreversible shift. The core contracts, raising temperature and density in a last attempt to sustain fusion. For a time, heavier elements such as silicon fuse into iron. Yet iron brings a quiet boundary to the process, because fusing iron does not release energy. Instead, it consumes energy, and the star cannot afford that cost. Without new outward pressure, the balance that held the star for so long collapses inward. Gravity pulls the core tighter, faster, and with a force that grows beyond anything the star has experienced before. You follow this inward motion, noting how rapidly conditions change. Within less than a second, the core contracts at a speed that defies ordinary experience. As density rises, electrons are squeezed into protons, forming neutrons and releasing neutrinos. This process, called electron capture, becomes overwhelming as the collapsing core approaches nuclear density. You imagine each particle forced closer until the matter resembles a giant atomic nucleus, packed so tightly that further compression becomes incredibly difficult. This resistance, known as neutron degeneracy pressure, plays a crucial role, because it is one of the few forces capable of halting gravitational collapse in these extreme conditions. Then, in the surrounding layers, the collapse creates a shock wave. Its behavior depends on many factors, including the star's mass and internal structure. Most of the core's gravitational energy escapes as a flood of neutrinos, nearly massless particles that carry away energy at extraordinary rates. In many cases, these neutrinos help revive the shock wave, driving it outward. You visualize this expanding wave sweeping through the star's outer layers, ejecting them into space. What follows is a supernova, an explosion so bright it can outshine an entire galaxy for a short time. Observatories detect these events by capturing light across many wavelengths, from visible to X-ray to gamma-ray. Each piece of data confirms the violent moment when a massive star's life ends. When the explosion clears, a compact object remains at the center. Its fate depends on mass. If the core is within a certain threshold, roughly up to about 2 to 3 times the mass of the Sun, neutron degeneracy pressure is strong enough to resist gravity. The object stabilizes into a neutron star, an incredibly dense remnant composed mostly of neutrons. You reflect on the precision of these limits, derived from theoretical models, nuclear physics experiments, and observations of binary systems where neutron star masses can be measured with remarkable accuracy. If the core is more massive than this limit, gravity overwhelms even neutron degeneracy pressure. No force currently known can halt the collapse, and the object continues inward until it forms a black hole. You picture this quietly, a region of space where gravity is so intense that not even light can escape. Its formation is silent, not because the event lacks power, but because nothing can communicate outward once the horizon forms. Observations of black holes rely on indirect evidence, such as how surrounding matter behaves, or how stars orbit an unseen mass with astonishing speed. To understand these outcomes, you consider the role of fundamental forces. Gravity works on all mass, drawing it inward. Nuclear forces push back under extreme conditions, especially when matter is compressed to densities found in neutron stars. The competition between these forces decides whether collapse stops or continues. This interplay shows how stars serve as laboratories for physics that cannot be recreated on Earth. Their behavior reveals details about matter under pressures far beyond any human-made experiment. As you follow this scientific story, the observational evidence becomes a comforting guide. Astronomers study supernova remnants, expanding clouds of gas and dust that still carry the signature of the explosion. In some remnants, a neutron star sits at the center, spinning rapidly and emitting beams of radiation detectable as pulsars. These signals provide precise timing information that confirms the object's mass, rotation, and magnetic field. In others, the remnant shows no compact star, suggesting that the core likely collapsed into a black hole. Measurements of surrounding gas, gravitational interactions, and high-energy emissions help confirm these conclusions. Instrument after instrument adds to the picture. X-ray telescopes reveal the hot surfaces of neutron stars and the energetic regions around black holes. Radio telescopes trace expanding supernova shells. Neutrino detectors, rare but growing in sensitivity, capture faint signals from distant stellar collapses, offering a direct glimpse into the moment when the core transforms. With each observation, the scientific foundation grows firmer, and your understanding becomes more grounded in evidence rather than imagination. You move deeper into the physics of collapse, noting how quickly the core changes state. Temperatures rise to billions of degrees, densities climb to levels comparable to atomic nuclei, and the matter inside behaves according to the rules of quantum mechanics. You follow these transitions gently, appreciating how layers of well-tested physics, general relativity, nuclear physics, particle interactions, converge to explain a single moment in cosmic history. Nothing here requires speculation. The data from countless stars, both living and dying, supports each step. The cycle of collapse and explosion enriches the cosmos. The heavy elements produced in the star's final moments disperse into interstellar space, later becoming part of planets, atmospheres, and even living organisms. You observe how this process links stellar death to future worlds, not through poetry, but through measured chemical signatures found in meteorites, stardust grains, and the atmospheres of ancient stars. It is a quiet reminder that the universe builds complexity through repeated generations of stars. As you rest with these ideas, the calm sense of continuity deepens. The collapse of a massive star is not only a dramatic endpoint, but also a doorway to the most extreme forms of matter known. Understanding how and why the collapse stops or does not stop opens the way to exploring the objects that result. In the soft quiet of this reflection, you sense how the behavior of matter at the threshold of gravitational dominance leads naturally to the study of what emerges when collapse settles into its final shape. You begin by picturing the quiet aftermath of a massive stellar collapse. The explosion has faded, leaving behind an object no larger than a city, yet more massive than the sun. You let your attention rest on this small remnant, noticing how gravity has compacted matter to a degree that challenges ordinary intuition. This object is a neutron star, a place where the familiar structure of atoms has been stripped away by immense pressure, leaving almost nothing but tightly packed neutrons. You imagine the moment when the collapsing core first stabilizes. As electrons are forced into protons, neutrons form in enormous numbers, creating a dense assembly of particles held together by gravity and supported by neutron degeneracy pressure. This pressure arises from quantum mechanics, from the rule that identical particles cannot occupy the same quantum state. You follow this principle gently, sensing how it becomes a natural counterforce against gravity when densities reach nuclear levels. It does not push outward through heat or fusion. It exists because of the fundamental behavior of matter itself. As the object settles, you feel the extreme conditions inside. The density is so high that a teaspoon of neutron star material would outweigh billions of tons on Earth. You picture this without exaggeration, understanding that the density comes from removing all empty space within atoms. Nuclei that once floated far apart compared to their size now merge into a single, continuous form of matter. Each neutron sits extremely close to its neighbors, held in place by nuclear forces that normally act only in atomic nuclei. Here, those forces operate across an entire star. The surface forms a thin, solid crust composed of unusual atomic structures. At lower densities, nuclei can still exist, though they are squeezed into exotic shapes that behave differently from those on Earth. As you trace deeper into the interior, those nuclei dissolve, and matter transitions into pure neutron-rich fluid. Some models describe additional components, such as superfluid neutrons or superconducting protons, not as speculation but as mathematical solutions that match observed properties. You let these possibilities pass softly through your mind, knowing they come from decades of careful physics and observational constraints. Now you imagine how this compact object spins. During collapse, the core conserves angular momentum, just as a figure skater spins faster by pulling in their arms. What was once a slowly rotating stellar core becomes a neutron star turning many times per second. Some spin hundreds of times per second, creating regular pulses of radiation detectable across vast distances. You follow this rotation, realizing how stable it is. The precision of these pulses rivals atomic clocks, making neutron stars some of the most reliable natural timekeepers known. You also consider the magnetic field. Compression intensifies the star's magnetic field lines, making them immensely strong. These fields can reach strengths billions of times greater than Earth's magnetic field. You picture radiation streaming along those magnetic axes, giving rise to lighthouse-like beams that sweep through space. When the beam crosses Earth, instruments detect a pulse. This is why neutron stars appear as pulsars, and these pulses serve as a window into their rotation, energy loss, and internal structure. Observations from telescopes confirm these behaviors. Radio arrays detect rhythmic pulses with remarkable stability. X-ray observatories, such as NICER on the International Space Station, measure small variations in brightness caused by hot spots rotating in and out of view. These variations help astronomers estimate the star's mass and radius, two values that reveal how matter behaves under extreme pressures. When the mass becomes too high for neutron degeneracy pressure to support, collapse continues into a black hole. But within a certain mass range, the object remains stable, standing at the boundary between matter and gravitational collapse. You explore the temperatures involved. Shortly after formation, neutron stars are incredibly hot, with surface temperatures reaching millions of degrees. Over time, they cool through neutrino emission and thermal radiation, though they remain warm enough to be detected in X-rays for millions of years. This cooling pattern offers clues about the star's interior composition, because different states of matter release heat in different ways. You follow this idea gently, recognizing how scientists match theory to observation to infer what the inner layers must be like. As your attention moves inward again, you consider the possibility of superfluidity. Under the extreme pressures and densities inside a neutron star, neutrons may behave as a single quantum fluid that flows without friction. This behavior explains sudden changes in rotation called glitches, where the star momentarily speeds up. You imagine these tiny adjustments happening quietly, governed by the motion of superfluid components within the crust and core. The data supporting this comes from decades of timing observations, showing consistent patterns across multiple neutron stars. You turn now to how neutron stars interact with their environment. Some gather matter from a companion star, forming an accretion disk. The incoming matter heats up and emits X-rays before reaching the neutron star's surface. Unlike black holes, neutron stars have a solid surface, so the accreted matter can produce bursts when it accumulates and undergoes thermonuclear reactions. These X-ray bursts are detected as sudden increases in brightness, lasting seconds or minutes. They provide direct evidence for the presence of a surface and help refine models of neutron star size and structure. Gravitational interactions also reveal their masses. In binary systems, neutron stars tug on their companions, causing measurable shifts in orbital timing. By tracking these shifts, astronomers determine mass with high precision. Most measured neutron stars fall between about 1.2 and 2.2 solar masses, though a few appear heavier. These measurements shape the understanding of what forms are possible inside the core. If a neutron star can remain stable above certain mass thresholds, It influences the physics of dense matter and the limits at which collapse becomes unavoidable. You reflect on how neutron stars act as laboratories of extreme physics. They embody conditions impossible to reproduce on Earth, allowing astrophysics to complement particle physics and nuclear physics. Observations from across the electromagnetic spectrum, as well as gravitational wave detections, refine the understanding of these objects. Their precise behavior under gravity, pressure, and magnetic fields becomes a guide to how matter behaves when compressed to the limit imposed by the laws of nature. In the calm space of this moment, you sense the stability and tension inside a neutron star. It does not explode outward, nor does it collapse inward. Instead, it sits balanced at the threshold where matter resists gravity through quantum mechanical pressure. This balance produces one of the universe's most remarkable states, where density reaches its limit and structure adjusts accordingly. You feel the quietness of this equilibrium, knowing it reflects the fundamental rules that shape the cosmos at its most extreme scale. As your thoughts rest with this understanding, you begin to appreciate how studying these compact stars reveals more than their own nature. Their properties, their emissions, and their interactions provide essential clues about how gravity behaves near dense objects, how matter organizes itself under intense pressure, and how energy is released in some of the universe's most powerful events. And with this gentle awareness, your attention naturally drifts toward the behavior of gravity itself, especially in places where even these remarkable forces begin to struggle against its pull. You begin by imagining a collapsing stellar core that has gone beyond the point where matter can resist gravity. The pressure that once held neutrons apart no longer succeeds. The mass is too great, the inward pull too strong, and nothing in known physics can halt the collapse. Gravity continues inward without pause, and you observe quietly as the material falls toward a state where escape becomes impossible. This is the birth of a black hole, an object defined not by what it contains, but by the behavior of spacetime around it. You let your attention move gently toward the idea of an event horizon. This horizon is not a surface in the usual sense. It is a boundary in spacetime. Once crossed, no signal, no particle, no photon can return. You notice how calmly this threshold exists, not as a wall, but as a region where the curvature of spacetime becomes so steep that all paths lead inward. You follow the concept slowly, allowing general relativity to guide the explanation. Mass curves spacetime, and when enough mass occupies a small enough region, that curvature deepens beyond recovery. You picture the collapsing core shrinking until its radius becomes smaller than the Schwarzschild radius, a value determined only by mass. For a black hole of one solar mass, this radius is just a few kilometers. For something millions of times heavier, like the black holes at the centers of galaxies, it expands to large scales, but the underlying physics remains the same. The horizon forms when the inward pull surpasses every possible outward influence. As the collapse continues, matter approaches a region of extreme density. General relativity predicts a singularity at this center, a point where density becomes infinite and the known laws of physics cease to describe conditions accurately. You acknowledge this not as speculation, but as a mathematical boundary in current theory. Observations do not probe the singularity, and no imagery depicts what lies within. Instead, science focuses on what can be measured from outside the horizon, where predictions align precisely with real data. You turn now to the observational methods that reveal these invisible objects. Because no light escapes, astronomers rely on indirect evidence. One method involves watching stars move around an unseen mass. In regions like the center of the Milky Way, stars orbit something extremely dense and massive yet invisible. Their motions follow predictable gravitational paths, allowing the mass to be calculated. The results consistently point to a supermassive black hole. You imagine these stars circling quietly, their movements providing some of the clearest evidence for black holes in the universe. Another method involves accretion disks. When gas spirals toward a black hole, friction and magnetic interactions heat it to millions of degrees. This glowing plasma emits X-rays and other radiation, which instruments detect. The pattern of emissions reveals the disk structure and motion. You picture the disk as a hot, rotating flow of matter, bright enough to study but never showing the black hole directly. The inner edge of the disk marks the last stable orbit before matter crosses the horizon. The behavior of these orbits matches predictions from general relativity, reinforcing the theory's accuracy. You also explore gravitational lensing. When light from a distant object passes near a black hole, its path bends due to the curvature of spacetime. Telescopes detect this bending as distorted or multiple images of the background source. You see how this effect provides yet another way to measure the mass and influence of black holes without relying on emitted light. The bending matches exact calculations from Einstein's equations, offering a calm, steady confirmation of the theory. Your attention shifts to what happens near the horizon. Time behaves differently there, slowing relative to regions farther away. If you watched an object fall toward the horizon from a great distance, you would see it appear to freeze, its light stretching into longer wavelengths. To the falling object itself, time would continue normally. This difference arises naturally from the geometry of spacetime. You let the idea settle gently, noticing how general relativity translates gravity into the shape of time as well as space. Rotating black holes add further structure. Many astrophysical black holes spin, carrying angular momentum from their parent stars or accreted material. A rotating black hole drags spacetime around with it, an effect called frame dragging. Near the black hole, this twisting becomes so strong that nothing can remain still relative to the distant universe. Observations of accretion disks and jet structures help confirm the presence of spin, matching theoretical models. You imagine this slow, powerful twisting of space, not chaotic but mathematically precise. Jets of high-energy particles often emerge from regions around rotating black holes. These jets do not come from inside the horizon. They form in the surrounding environment where magnetic fields, rotation, and inflowing plasma interact. You follow how particles accelerate along magnetic lines and escape far into space. These jets are visible across enormous distances and offer another way to study black hole behavior. They arise naturally from the physics of disks and magnetic fields, not from anything mysterious inside the black hole. As you continue reflecting, you consider how gravitational waves contribute to the understanding of these objects. When two black holes spiral together and merge, they send ripples through spacetime. These ripples carry information about mass, spin, and orbital motion. Detectors like LIGO and Virgo measure those waves directly, providing some of the strongest evidence for black holes. The shapes of the waves match predictions from numerical relativity, a field that solves Einstein's equations through computational methods. You let the idea of spacetime vibrations settle softly, knowing they confirm the existence and properties of black holes in a direct, physical way. You picture the merger of two black holes producing a final, larger black hole that settles into a stable form. The ringing of spacetime following the merger resembles the vibration of a struck bell, though at frequencies far higher than human senses can detect. These vibrations, called ring-down signals, fade as the black hole reaches a steady configuration. Again, the data align precisely with theoretical predictions, reinforcing your confidence in the underlying physics. Black holes also influence their surroundings through gravitational energy. Their presence shapes the motion of stars, gas clouds, and even entire galaxies. Supermassive black holes typically sit at galactic centers, and their growth connects to star formation and galactic evolution. Observations of these relationships emerge from decades of study, showing how black holes, despite their invisibility, play essential roles in cosmic structure. You sense how quietly yet profoundly they influence the universe, guiding the movement and distribution of matter on enormous scales. Despite their extreme nature, black holes behave predictably. Their properties depend on only a few measurable quantities: mass, spin, and charge. In astrophysics, charge is usually negligible, so mass and spin become the defining characteristics. You note how simple this description is compared to the complexity of ordinary stars. A black hole lacks surface, atmosphere, or internal layers. Everything collapses into a region defined by geometry alone. This simplicity makes them powerful tools for testing fundamental physics. As you rest with these ideas, you feel how gravitational collapse leads to an object that merges physics and geometry into a single form. The horizon marks the limit where escape becomes impossible, yet the space outside remains fully observable. Through careful measurement of light, matter, and gravitational waves, black holes reveal their presence without needing to be seen directly. In the quiet space of this reflection, your mind drifts toward the contrast between these objects and other compact remnants. Understanding how gravity behaves when matter compresses without limit naturally guides your attention to the environments that form around such extreme objects, where matter heats, glows, and spirals in the presence of overwhelming curvature. You begin by returning to the environment of a newly formed neutron star, still settling into its dense and compact state. The gravity is immense, the rotation fast, and the magnetic field already powerful. As you let the scene grow clearer, you notice that some neutron stars develop magnetic fields far stronger than others. These become magnetars, objects that hold the most intense magnetic fields known in the universe. Their fields can reach 1,000 times the strength of typical neutron stars, rising to values near 10 raised to power 14 or 15 Gauss. You take a moment to compare this to Earth's magnetic field, which measures less than 1 Gauss. The difference is so large it almost defies intuition, yet it is supported thoroughly by measurements and theory. You picture how such immense magnetic fields originate. During the collapse of the stellar core, magnetic field lines compress dramatically. Conservation of magnetic flux causes the field strength to rise, just as rotating contraction speeds up a skater's spin. In some cases, the field amplifies further through processes in the fluid interior, forming a dynamo effect on a scale unmatched anywhere else. You follow these ideas gently, knowing they emerge from established physics involving rotation, convection, and plasma behavior. As the magnetar cools, its crust forms, a rigid outer layer only a kilometer thick, but capable of holding enormous magnetic stresses. When these stresses exceed the crust's ability to cope, it fractures. You imagine a quiet starquake spreading across the surface, releasing energy in a burst of X-rays or gamma rays. Observatories such as Swift and Fermi detect these bursts as sudden flares, sometimes lasting only milliseconds. The signals show rapid rise times, consistent with the quick release of magnetic energy stored in the crust. Nothing in the behavior is speculative. It matches well-understood physics of magnetic stress and solid-state failure under enormous pressure. You explore how magnetars also show persistent X-ray emission, powered not by accretion or fusion but by magnetic energy gradually leaking from the interior. As the magnetic field slowly rearranges itself, it heats the crust and upper layers, producing steady radiation. You follow this slow release of energy, understanding that the field evolves over thousands of years. This evolution is measured through changes in rotation rate and observed luminosity. Magnetars tend to spin down quickly due to their strong magnetic fields, which act as a braking mechanism. By measuring the rate of this slowdown, astronomers infer magnetic field strength with remarkable precision. Now your attention shifts to pulsars, another class of neutron stars whose magnetic fields and rotation produce regular, predictable beams of radiation. You picture a neutron star rotating many times per second, its magnetic poles not aligned with its rotation axis. Along those magnetic poles, charged particles accelerate and emit radiation. As the star spins, these beams sweep through space like the rotating beam of a lighthouse. When one of the beams passes Earth, telescopes detect a pulse. You appreciate how these pulses are extraordinarily stable, acting like natural cosmic clocks. Radio pulsars emit pulses in radio wavelengths, which travel freely through interstellar space. Observatories measure their timing with microsecond precision. These signals reveal everything from rotation rates to interactions with surrounding plasma. Some pulsars rotate so quickly they are called millisecond pulsars, spinning around hundreds of times per second. They reach these speeds by accreting matter from a companion star, transferring angular momentum over millions of years. You follow this process calmly, knowing it is supported by both theoretical modeling and decades of observation. There are also X-ray pulsars, where the pulses arise not from radio beams but from hotspots on the neutron star's surface. These hotspots form when matter from a companion falls onto the magnetic poles. As the star rotates, the hotspots come into and out of view, creating periodic signals in X-ray wavelengths. Instruments like NICER detect these variations and use them to measure the star's size and mass. You notice how each of these data points helps refine the understanding of dense matter physics. You reflect on the difference between magnetars and pulsars. Pulsars emit regular pulses because of their rotation and magnetic alignment, while magnetars produce bursts because of their extreme magnetic stresses. Some objects show characteristics of both, revealing the diversity of neutron star behavior. The classification emerges from observed properties, not from arbitrary labels. It demonstrates how magnetic field strength, rotation rate, and crust structure shape the star's appearance across the electromagnetic spectrum. As you rest with these ideas, you turn again to the measured effects of rotation. Pulsars slow down gradually over time, losing rotational energy through radiation and magnetic braking. By tracking this slowdown, astronomers learn not only the magnetic field strength but also the age of the pulsar. Young pulsars spin quickly, while older ones rotate more slowly. This connection between rotation and age is known as the spin-down age. You find comfort in this orderliness, where precise timing reveals the quiet passage of cosmic time. You also consider how pulsars serve as probes of the interstellar medium. Radio pulses travel through interstellar plasma, experiencing delays that depend on electron density along the path. By measuring these delays, astronomers map the distribution of plasma in the galaxy. Pulsars, in this way, become tools not only for understanding neutron stars but for studying the structure of the galaxy itself. They offer a steady stream of information, each pulse carrying subtle signatures of the space it has crossed. Binary pulsars provide another opportunity to test physics under extreme conditions. When a pulsar orbits another neutron star or a white dwarf, precise timing of the pulses reveals orbital decay caused by gravitational wave emission. These measurements provided early confirmation of general relativity long before gravitational waves were detected directly. You sense how the timing of pulses functions like a continuous experiment, running for decades, verifying predictions with calm regularity. Magnetars, too, offer insight into how matter behaves under extreme magnetic environments. Their bursts and persistent emission patterns give clues about crust thickness, magnetic field decay, and internal composition. They reveal how nuclear physics and magnetic physics interact under conditions far beyond laboratory experiments. These interactions lead to models that continue to evolve as new data arrives from X-ray and gamma-ray observatories. In the quiet stillness of this reflection, you feel how the behavior of neutron stars expands your understanding of matter under extraordinary pressures and magnetic forces. These objects do not rely on imagination or speculation. Their signals reach Earth clearly, carrying information about their rotation, magnetic fields, and internal dynamics. Observations remain consistent with well-established physics, showing how nature expresses fundamental laws in some of the most extreme environments. As your thoughts settle, the image of a neutron star becomes more complete. The dense core, the magnetic fields, the bursts, the pulses, and the quiet rhythms of rotation. These features prepare your mind to explore another aspect of extreme astrophysics, where gravity shapes the environment around compact objects and alters the flow of time and energy in ways that become measurable and deeply revealing. You begin by imagining the space just above a neutron star's surface, a region where gravity reaches levels far beyond anything Earth can produce. The surface gravity is hundreds of billions of times stronger than what you feel on the ground beneath your feet. You allow this idea to settle softly, not as a dramatic image, but as a measured description of how mass and radius shape gravitational strength. The neutron star's small size and large mass combine to create an environment where even light struggles to climb away. You let your attention move toward a fundamental prediction of general relativity. Gravity affects not only motion but also time and light. Near a neutron star, time passes more slowly relative to regions far away. This difference, called gravitational time dilation, arises naturally from the curvature of spacetime around massive objects. You picture a clock resting on the neutron star's surface, ticking at a slower rate than a clock in empty interstellar space. No physical damage occurs to the clock. The slower ticking is simply a result of how time flows in curved spacetime. This concept has been confirmed countless times, even on Earth with sensitive experiments. In stronger gravitational fields, the effect grows more pronounced. You explore gravitational redshift next. When light leaves a region of strong gravity, it loses energy. This loss shows up as an increase in wavelength. Light emitted from the surface of a neutron star arrives at distant detectors shifted toward the red end of the spectrum. The amount of redshift depends on how deep the light originates within the gravitational field. X-ray observatories measure these shifts in spectral lines, allowing scientists to estimate the mass and radius of neutron stars. The data agrees with theoretical predictions, offering a quiet confirmation of relativity's accuracy under extreme conditions. You turn your attention to escape velocity. On Earth, this value is a few kilometers per second. On a neutron star, the required speed approaches half the speed of light. This does not mean objects leap off the surface. It simply describes the energy required for any particle or photon to move outward against the star's gravitational pull. The concept helps explain why neutron stars appear as they do. Their radiation emerges with difficulty, shaped by gravity's influence as it travels outward. As you rest with these ideas, you consider how space itself curves around these dense objects. In general relativity, gravity is not a force in the traditional sense. Instead, it is the shape of spacetime guiding the motion of matter and light. You imagine spaces near neutron stars as regions where straight-line paths bend naturally. If you could watch a beam of light pass close to the surface, you would see it deflect in response to the curvature. Telescopes observe this bending in many astrophysical environments, reinforcing the idea that spacetime geometry provides an accurate framework for understanding gravity. You gently shift your focus toward black holes, where curvature becomes even more extreme. Approaching the event horizon, gravity grows so strong that all paths lead inward. Time dilation becomes enormous. To someone far away, processes near the horizon appear to slow almost to a standstill. You follow this effect carefully, recognizing that for an object falling inward, time flows normally. The difference arises from the geometry of spacetime, not from any physical resistance or obstacle. It is a calm, consistent result of the mathematical structure of relativity. You also reflect on gravitational lensing. When light from a distant object passes near a massive source, the curved spacetime bends its path. This bending creates distorted images or multiple images of the original source. Astronomers measure these distortions to estimate masses of galaxies, clusters, and black holes. Observations align precisely with calculations from general relativity, confirming the theory's predictions at both cosmic and compact object scales. You imagine light weaving gently through warped space, following the natural pathways carved by gravity. Another effect emerges from the behavior of particles near strong gravitational fields. In the space around neutron stars and black holes, particles follow curved trajectories that differ from anything seen on Earth. The paths trace orbits shaped by intense curvature. Some regions allow stable orbits, others do not. Near black holes, especially around rotating ones, spacetime twists, creating regions where motion becomes tied to the rotation. This phenomenon, called frame dragging, causes matter and light to follow the spinning geometry. Observations of accretion disks and jet orientation provide evidence for this twisting, matching detailed theoretical models. You also consider how time delays in pulsar signals provide insight into gravity. When pulses pass near massive objects, their travel time changes slightly. These delays match predictions from relativity and help astronomers map gravitational fields with remarkable precision. Binary pulsars provide especially clear data. As pulses travel through the curved spacetime of a companion star's gravitational field, their timing shifts in predictable patterns. These measurements reveal masses, orbital parameters, and the strength of gravitational effects. You appreciate how consistent these observations are, each pulse reinforcing the theory in a calm, steady rhythm. As your understanding deepens, you reflect on the smoothness of general relativity's predictions. Nothing in these effects requires speculation or assumption beyond the theory itself. The curvature of spacetime, the influence on time and light, and the behavior of matter all arise naturally from its equations. Observations from telescopes, detectors, and timing systems repeatedly confirm these behaviors. This harmonic alignment between theory and measurement reveals a quiet precision underlying even the universe's most extreme environments. You think of the region just above a neutron star's surface again. The curvature there shapes everything. The direction of light, the flow of time, the motion of matter, and the escape of radiation. The star's structure and appearance depend not only on internal pressure but also on the geometry surrounding it. You sense how the combination of nuclear physics inside the star and gravitational physics outside the star creates a complete picture, each part supporting the other. In the soft quiet of this reflection, your thoughts drift toward how gravity guides matter and energy when they fall inward. Understanding these extreme gravitational environments naturally leads to the study of what happens when matter spirals closer, heats up, and emits radiation in response to friction and magnetic forces, revealing yet another dimension of the universe's most compact objects. You begin by imagining a quiet stretch of space where gas from a nearby star drifts toward a compact object. The flow at first appears gentle, a slow movement guided by gravity. But as the gas approaches a neutron star or black hole, it cannot fall straight inward. Instead, it carries angular momentum, a kind of rotational motion that prevents it from plunging directly into the center. You picture the gas forming a broad, thin disk around the compact object, each particle moving in an orbit that brings it gradually closer. This structure is an accretion disk, a place where matter transforms gravitational energy into heat and light. You let your attention settle on the disk's rotation. Particles closer to the center orbit faster than those farther out. This difference in speed generates friction and turbulence within the disk. Although the gas itself is thin, the cumulative effect of countless interactions heats the material to extreme temperatures. Near a neutron star or stellar mass black hole, temperatures rise into the millions of degrees. At these energies, matter emits radiation in X-rays and ultraviolet light. You follow this steady rise in temperature, understanding it not as a sudden ignition but as a consequence of orbital physics and friction within the disk. Magnetic fields add another layer of structure. Even small magnetic fields in the gas can become amplified by the disk's rotation. These fields stir the material, enhancing turbulence and helping transport angular momentum outward. This process, supported by decades of theoretical modeling and simulations, allows matter to drift inward. Without this redistribution of angular momentum, the gas would remain in orbit indefinitely. You reflect on how magnetic fields, though invisible, play a guiding role in shaping the disk's behavior. As matter moves inward, it releases gravitational energy. The closer it gets to the compact object, the more energy becomes available. Just before reaching the neutron star's surface or crossing a black hole's event horizon, the energy release reaches its peak. You imagine a region of intense heating known as the inner accretion disk, where particles orbit at tremendous speeds and temperatures reach their maximum. The radiation emitted from this region carries information about the compact object's mass, spin, and gravitational environment. When the central object is a neutron star, the gas eventually collides with a solid surface. This impact produces a burst of energy as the material decelerates abruptly. The surface heats unevenly, creating hotspots that rotate into and out of view. X-ray telescopes detect this rotation as periodic brightness changes. These signatures allow astronomers to measure the neutron star's radius and magnetic field structure. You observe how the presence of a surface introduces distinctive behavior to the disk's radiation. In contrast, a black hole has no surface. Gas that reaches the inner edge of the disk continues inward past the event horizon, disappearing from view. Because there is no sudden deceleration at a surface, the radiation primarily comes from the disk itself rather than from a final impact. This difference helps astronomers distinguish neutron stars from black holes, even when they cannot see the central object directly. You let this comparison settle into your mind, appreciating how nature reveals its structure through measured energy rather than appearance. You shift your focus to how telescopes observe these disks. Instruments such as Chandra, XMM Newton, and NuStar detect X-rays emitted by the hot, inner regions. The brightness and spectrum of the radiation reveal the disk's temperature at different distances from the center. By fitting these observations to well-tested physical models, astronomers estimate the mass and spin of black holes and neutron stars. Timing analysis uncovers oscillations in the disk, sometimes linked to instabilities or resonances within the flow. These oscillations appear as subtle variations in brightness and provide insight into the underlying gravitational environment. Accretion disks also show spectral lines that shift due to gravity and motion. As light climbs out of a strong gravitational field, it becomes redshifted. Additionally, the rapid orbital motion causes Doppler shifts that broaden the spectral lines. The combined effect creates a characteristic pattern known as a relativistic line profile. Observing these profiles allows scientists to measure how fast the disk rotates and how close matter orbits to the compact object. You follow this interplay of gravitational redshift and Doppler motion, noting how these effects form predictable patterns that match the predictions of relativity. In systems where a compact object pulls matter from a companion star, the flow can become irregular. Sometimes the disk becomes unstable, leading to sudden increases in brightness called outbursts. These occur when stored material in the disk heats suddenly and begins to flow inward more rapidly. Observations track these changes over days or weeks, capturing the evolving structure of the disk. You sense how even in dynamic states, the physics of accretion follows consistent rules based on temperature, density, and angular momentum. Jets may also form near some accreting black holes and neutron stars. These jets arise not from within the compact object but from the environment around it. Magnetic fields, rotation, and infalling matter interact to accelerate particles along narrow paths extending far into space. Radio telescopes observe these jets as long, thin beams that often travel at speeds close to the speed of light. The details of jet formation remain an active area of research, but the overall process aligns with plasma physics and magnetic field behavior in strong gravitational environments. As your thoughts settle, you reflect on how accretion disks transform the hidden presence of compact objects into visible signals. Neutron stars and black holes do not emit light on their own. Their gravitational influence shapes the flow of matter around them. The disks act as intermediaries, converting gravitational potential energy into radiation that reaches Earth. Each spectrum, pulse, and flare becomes a measurable clue. These observations allow scientists to study environments where gravity, heat, and magnetic fields reach their most extreme levels. You consider how the structure of the disk depends on the compact object it surrounds. The presence or absence of a surface determines how the flow ends. The intensity of radiation reveals temperature. The shape of spectral lines exposes orbital speed and gravitational curvature. The timing variations trace instabilities and interactions within the disk. All these factors combine to create a detailed picture built entirely on observation and physically tested models. In the calm space of this understanding, you begin to sense how matter behaves not only as it orbits, but as it collides, heats, and glows in the presence of overwhelming gravity. This gentle awareness naturally leads your attention toward the next realm of extreme astrophysics, where collisions between compact objects release energy that reshapes elements and sends ripples through spacetime. You begin by imagining two neutron stars locked in orbit around one another, circling through space in a quiet but relentless dance. Each one is only about the size of a city, yet each contains more mass than the sun. The gravity between them is immense, shaping their motion into precise, predictable paths. As you follow their orbits, you notice that they slowly draw closer. They lose a small amount of energy each second, not through friction or radiation in the ordinary sense, but through gravitational waves, ripples in spacetime that carry energy outward at the speed of light. These waves were predicted by general relativity and confirmed directly a century later. In a binary neutron star system, their presence gradually tightens the orbit. You imagine the stars circling faster as the distance between them shrinks. The outer layers distort slightly from tidal forces, creating subtle changes in shape that continue to intensify as they approach one another. This process is slow at first, unfolding over millions of years. But as the stars draw close, the spiral accelerates, and orbital periods drop from hours to minutes, then from minutes to seconds. You focus now on the final moments before collision. the stars accelerate to a significant fraction of the speed of light. Gravitational waves grow stronger, forming a rising signal in frequency and amplitude. Detectors such as LIGO and Virgo have captured these signatures, not as imagined patterns, but as measurable vibrations in the fabric of spacetime. The data reveals precise information about the masses, distances, and orbital patterns of the merging stars. You let this knowledge settle, grounded in observation rather than speculation. As the stars touch, their surfaces meet with extreme force. Matter compressed at nuclear density begins to tear away, forming streams of neutron-rich debris. These streams do not behave like ordinary fluid. They respond to gravity, nuclear forces, and rapid rotation in ways that have been modeled through detailed physics and confirmed indirectly by observations of kilonovae. You picture the debris spreading outward, forming hot, expanding clouds of material that will soon create elements unknown in simpler environments. Inside this expanding matter, the conditions become ideal for rapid neutron capture, known as the R process. You let the idea emerge gently. Atoms build heavier nuclei by capturing neutrons faster than they can decay. This process requires environments that are both extremely dense and rich in free neutrons. Neutron-star collisions provide precisely that. The nuclei assemble into heavy elements such as gold, platinum, thorium, and uranium. These elements cannot form through ordinary nuclear fusion. They require the extreme conditions present in this moment. You follow the expanding ejecta as it heats and cools. As it moves outward, the nuclei stabilize, locked into forms that will last billions of years. This is the origin of many of the heaviest elements found in the universe. When you think of gold in a ring or platinum in a laboratory instrument, you are witnessing material forged in an event like this billions of years ago, in environments far removed from ordinary stellar processes. The abundance of these elements in Earth's crust and meteorites supports the conclusion that neutron-star mergers play a major role in creating them. As the debris expands further, it radiates light, a kilonova. You picture this glow, not as a bright explosion like a supernova, but as a steadily evolving burst of light shaped by radioactive decay. As the newly formed nuclei release energy, the ejecta warms and emits optical and infrared radiation. The brightness and color of a kilonova reveal which elements are present and how much matter was ejected. Observatories across the world captured such light from GW 170817, the first neutron-star merger observed through both gravitational waves and electromagnetic radiation. This event provided direct evidence for the creation of heavy elements. You imagine the kilonova from a scientific distance, its light fading gradually over days and weeks. Astronomers recorded a spectrum rich in signatures consistent with R process elements. The match between prediction and observation offers one of the strongest confirmations of how these elements originate. You let this alignment between theory and data form a calm sense of clarity. The universe creates its heaviest atoms in the collision of compact stars. After the collision itself, a new compact object forms at the center of the debris cloud. Its fate depends on mass. In some cases, the merged remnant becomes a rapidly spinning neutron star temporarily supported by rotation. In others, the combined mass exceeds the limit neutron degeneracy pressure can uphold, and the object collapses into a black hole. The transition between these possibilities lies in a narrow range of masses determined through nuclear physics and astrophysical modeling. Observations of gravitational wave signals help refine these limits, offering insights into matter compressed beyond nuclear density. You now reflect on how gravitational waves recorded from neutron-star mergers differ from those detected from black hole mergers. The waveforms contain information about tidal deformability, how easily a neutron star is stretched by gravitational forces. This property depends on the internal structure of the star, including the stiffness of dense matter. By studying these waves, scientists gain clues about the equation of state of neutron-star matter, a central question in modern astrophysics. You sense how this event becomes both a cosmic furnace and a laboratory for fundamental physics. Your attention shifts to the behavior of magnetic fields during the collision. As the neutron stars spiral inward, their magnetic fields can intensify through compression and turbulence. In some models, this amplification produces strong magnetic winds and contributes to the formation of short gamma-ray bursts. Observations support this connection. A brief flash of gamma rays was detected less than 2 seconds after GW 170817. The timing and direction align with predictions about how jets might emerge from the remnant. You allow this link to settle, understanding it as part of a broader pattern in which multiple forms of observation combine to tell one coherent story. You think now of the material thrown into space. It travels outward, mixing with interstellar gas over millions of years. Eventually, it becomes part of future stars, planets, and rocky worlds. The heavy elements created in this merger enrich the galaxy, contributing to the chemical diversity seen in old stars and planetary systems. Evidence of our process elements appears in the spectra of ancient stars and in isotopes found in meteorites. These findings support the idea that neutron star collisions have occurred repeatedly throughout the history of the Milky Way. As your thoughts drift through this quiet understanding, you reflect on the gentle rhythm underlying such powerful events. The collision is not chaotic from the viewpoint of physics. It follows the rules of gravity, nuclear interactions, and thermodynamics. The radiation, waves, and particles each carry information that can be measured and understood. Nothing in this process requires speculation. Every step arises naturally from well-established principles and is confirmed through observation. You return once more to the image of two neutron stars orbiting one another in darkness. Their long spiral leads to a moment of fusion, not in a furnace of hydrogen, but in the compressed matter of nuclear density. Their final act shapes the periodic table itself, providing the universe with elements needed for planets, life, and technology. You feel the quiet certainty of this process, grounded in data yet vast in implication. In the stillness of this reflection, your mind traces how energy, matter, and gravity intertwine when compact stars collide. This gentle awareness opens into an understanding of other gravitational interactions, including those involving black holes, whose mergers generate waves of pure curvature moving silently through the cosmos. You begin by imagining two black holes orbiting one another, their presence revealed not through light, but through the motion of spacetime itself. Each black hole curves the surrounding fabric, creating a dynamic landscape in which their orbits slowly decay. There is no surface, no solid crust, no magnetic flare to mark their presence. Instead, gravity communicates entirely through geometry. As you follow their motion, you notice how they circle steadily, losing energy in the form of gravitational waves, ripples that travel outward at the speed of light. At large distances, the waves are faint, carrying only a small fraction of the system's energy. But as the black holes draw closer, their motion quickens. The orbital period shortens, and the amplitude of the waves grows. You picture the pair spiraling inward, not with sudden shifts, but with a smooth, predictable tightening. This spiral follows calculations from general relativity so precisely that numerical relativity simulations match observational data to extraordinary accuracy. The physics guiding this motion depends only on mass, spin, and geometry, giving the system a clarity not found in more complex astrophysical environments. You let your attention drift toward the structure of the waves themselves. As the black holes orbit, they imprint a rhythm onto spacetime. The waves begin as low-frequency signals, rising gradually in pitch as the spiral accelerates. This shape, known as a chirp, has been observed by gravitational wave detectors. Each chirp encodes the story of the merging black holes, revealing their masses and the distance at which the merger occurred. The signals appear faint on Earth, altering distances by less than a fraction of a proton's width. Yet the detectors measure them with remarkable sensitivity. The first confirmed detection of black hole merger waves arrived in 2015. The signal matched exactly what general relativity predicted. It rose in a smooth, continuous curve, reaching a peak as the black holes touched and merged. Afterward, the waveform transitioned into a brief, fading oscillation known as ringdown, the final stage where the newly formed black hole settles into a stable shape. You imagine this ringdown as spacetime gently vibrating before returning to calm. The frequencies and decay rates of these vibrations match precise theoretical calculations. You now picture the moment when the two horizons meet. There is no collision in the usual sense. Since black holes have no surfaces, Their merger involves the fusion of horizons rather than the impact of matter. The horizons stretch and distort as they join, then relax into a single, larger horizon. The energy released in gravitational waves during this moment can equal several times the mass of the Sun, converted entirely into spacetime curvature. This process is free of light or heat. The energy radiates only as gravitational waves, the purest form of gravitational communication. You explore how spin shapes the merger. If either black hole spins, it drags spacetime around with it. The orientation and magnitude of these spins influence the motion of the inspiral. When spins align with the orbital axis, the inspiral proceeds steadily. When they misalign, the orbital plane can precess, causing the signal to modulate. These variations, observed in multiple detections, allow scientists to infer the orientation and rotation of the black holes. The behavior arises naturally from general relativity and has been confirmed by detailed waveform analysis. As you follow the aftermath, you observe how the final black hole settles into a stable state defined by only two properties: mass and spin. This simplicity emerges because black holes lack internal structures. Any irregularities produced during the merger radiate away as gravitational waves, leaving the black hole smooth and symmetrical. This final configuration embodies the idea that black holes are governed by clean, geometric principles. The surrounding spacetime becomes quieter as the waves fade into the background. You consider how detectors capture these faint signals. LIGO and Virgo use long vacuum arms and laser interferometry to measure tiny shifts in length as gravitational waves pass through Earth. When a wave stretches one arm and compresses the other, the interference pattern of the lasers changes slightly. These changes are recorded and analyzed. You imagine the waves traveling millions of light years before arriving at Earth, yet still carrying a precise imprint of the merger. The signal's clarity depends on the nature of spacetime itself, which transmits the waves without scattering or absorption. These detections mark the beginning of gravitational wave astronomy. Black hole mergers occur frequently in the universe, and each event adds to the growing catalog of observed signals. The distribution of their masses, spins, and distances provides insight into how black holes form and evolve. Some black holes appear heavier than those formed in ordinary stellar evolution, suggesting the possibility of hierarchical mergers, black holes merging more than once. Other signals hint at precession or spin dynamics that reveal the history of the systems involved. You reflect on how these observations connect with numerical relativity. Scientists solve Einstein's equations on supercomputers to model the inspiral, merger, and ringdown. The resulting waveforms match the detections in exquisite detail, reinforcing confidence in the theory. Each successful match strengthens the understanding that gravity behaves consistently, even in the most extreme environments. This agreement between simulation and observation offers a sense of calm assurance. The absence of electromagnetic radiation in black hole mergers creates a unique observational signature. Unlike neutron star collisions, which produce kilonovae and gamma rays, black hole mergers communicate only through gravity. This simplicity allows scientists to isolate gravitational physics without the complications of matter, heat, or magnetic fields. You appreciate this clarity, noting how it provides a baseline for understanding more complex systems. Occasionally, a black hole merger may interact with surrounding matter, but the gravitational signal itself remains unaffected. The waves transmit only information about the motion of the black holes. They reveal nothing about the interior, because the interior remains hidden behind the event horizon. This consistent barrier ensures that black holes remain defined solely by external properties. As your thoughts settle, you consider how gravitational waves travel outward across the universe. They pass through galaxies, stars, and interstellar gas without disturbance. Their stability makes them excellent tools for exploring distant regions of space and time. Each detection extends the map of cosmic events and improves the understanding of how gravity shapes the universe on the largest scales. You return to the image of two black holes spiraling together in darkness. Their merger is silent, not because it lacks power, but because the energy emerges in a form that does not create light. The waves carry information directly through spacetime, reaching Earth long after the event has concluded. You find a quiet sense of awe in this process, knowing it represents gravity acting at its most fundamental level. In this calm reflection, your thoughts drift toward how these waves compare to signals from other cosmic collisions, especially those involving neutron stars, where matter, heat, and magnetic fields add layers of complexity and light to the gravitational story. You begin by imagining a neutron star and a black hole orbiting each other in deep space. The neutron star is incredibly dense, held together by the pressure that resists further collapse. The black hole, compact and dark, curves space-time so strongly that nothing escapes once it crosses the horizon. As they move through their orbit, they create a pattern of gravitational waves that slowly removes energy from the system. This loss is small at first, but it steadily shrinks the orbit over millions of years. As the objects draw closer, the neutron star feels the pull of tidal forces. You picture these forces stretching the star slightly along the line connecting the two bodies. The effect increases as the separation decreases. The neutron star's structure, supported by the quantum rules that govern dense matter, can resist these distortions up to a point. Beyond this, the star begins to deform more noticeably. The outcome depends on the masses involved and the spin of the black hole. A rapidly spinning black hole can alter the tidal environment significantly, bringing the tidal disruption radius farther out. You follow the spiral as it accelerates. The orbital period drops from minutes to seconds, and the gravitational wave frequency rises accordingly. Detectors on Earth would record this signal as a characteristic chirp, similar to those produced by other mergers but marked by subtle differences. These differences come from tidal deformability, the degree to which the neutron star stretches under gravitational influence. The waveform carries this imprint. Scientists analyze these changes to infer properties of neutron star matter and the behavior of gravity in strong fields. As the neutron star approaches the black hole, two possible outcomes arise. In the first, the neutron star plunges into the black hole intact, crossing the event horizon before being torn apart. If this happens, the gravitational wave signal ends abruptly, with no accompanying electromagnetic light. The star disappears entirely, and the merger leaves behind only a larger black hole. This outcome is more common when the black hole is much more massive than the neutron star. In the second outcome, the tidal forces exceed the neutron star's structural strength before it reaches the horizon. The star begins to tear apart, releasing neutron-rich debris. You imagine this disruption not as a dramatic explosion, but as a rapid transformation governed by deep gravitational gradients. The matter spreads into a dense spiral of ejecta around the black hole. Some of this material forms a temporary disk. Some is thrown outward into space. This environment offers conditions similar to neutron-star collisions, enabling the creation of heavy elements through the R process. You focus on the geometry of the debris. The distribution depends on the black hole's spin and the orientation of its rotation. A high spin aligned with the orbital plane allows the neutron star to approach more closely before crossing the horizon, increasing the chance of disruption. This interplay of gravitational and rotational effects determines how much matter escapes the black hole's pull. Observational evidence helps refine these models, showing how real mergers behave. If enough matter remains outside the black hole, the ejecta emits light. You picture this as a faint kilonova, dimmer than those produced by neutron star pairs but still detectable under favorable conditions. The brightness and color depend on the amount and composition of the material. Radioactive decay of the newly formed nuclei heats the ejecta, producing light that gradually fades. Astronomers model these signatures to determine whether a black hole-neutron star merger occurred and how much matter was ejected. You consider how gravitational waves provide additional information. The final moments of the waveform reveal whether disruption occurred. A sharp cutoff often indicates direct swallowing, while modifications in the late-in-spiral signal can suggest tidal effects. Events such as GW200105 and GW200115, detected in 2020, offer examples of systems that match the expected patterns for black hole-neutron star mergers. One appears to involve direct swallowing. The other may have allowed partial disruption. These interpretations come from detailed waveform analysis supported by established physics. You now shift to the behavior of spacetime near the black hole's horizon. For the neutron star, the approach is rapid. As it moves inward, tidal forces increase sharply. If disruption begins, the star stretches and breaks apart on timescales of milliseconds. If not, the horizon envelopes it silently. There is no physical barrier, only a region from which escape becomes impossible. You let this idea settle, noting how general relativity provides a consistent, well-tested framework for these descriptions. The presence of a neutron star allows electromagnetic signals to accompany gravitational waves, but only when disruption produces material outside the horizon. In some cases, magnetic fields from the neutron star interact with the debris, generating short-lived bursts of radiation. These emissions give additional insight into the dynamics of the merger. Their absence does not contradict the model. It simply indicates that the star crossed the horizon intact. You reflect on the interplay between nuclear physics and gravity. The neutron star's fate depends on the stiffness of dense matter, the equation of state. A stiffer equation of state allows the star to resist tidal stretching longer, increasing the chance of disruption. A softer one allows earlier deformation, changing the distribution of ejecta. Gravitational wave observations help constrain these possibilities by revealing how much the star deforms in the final moments. Each detection adds a piece to the larger puzzle of how matter behaves at the highest known densities. Your attention drifts toward the environment that forms after the merger. If debris remains, it can form a temporary accretion disk around the black hole. This disk evolves quickly, heating and cooling as matter falls inward. It may produce jets or outflows depending on the magnetic structure of the system. These features require no speculation. They arise from the same physics seen in other accreting systems, modified only by the extreme conditions present here. You also consider how black hole neutron star mergers contribute to the chemical enrichment of galaxies. Though they may produce less ejecta than neutron star pairs, they still create heavy elements that spread into interstellar space. Over millions of years, this material becomes part of new stars and planets. The evidence for such enrichment appears in the elemental patterns of ancient stars, consistent with contributions from multiple types of compact object mergers. As you let these ideas flow quietly, you feel how the meeting of a neutron star and a black hole becomes a natural extension of earlier processes. The physics remains grounded in observation and well-tested theory. The gravitational waves carry information about masses, spins, and tidal deformability. The light, when present, reveals the behavior of neutron-rich ejecta. Together, these signals offer a complete and consistent picture of the event. You return to the image of the two bodies circling one another, the neutron star small and bright, the black hole dark and compact. Their spiral ends in a moment governed entirely by the rules of gravity and nuclear physics. Whether the star is swallowed whole or torn apart depends on measurable properties rather than mystery. Each outcome fits within a broader understanding of the universe's most extreme environments. In the quiet of this reflection, your thoughts trace how compact objects interact through gravity, energy, and matter. This gentle understanding leads smoothly into the broader comparison of the physical extremes these objects represent, revealing how nature expresses violence and stability through different combinations of mass, density, and curvature. You begin by imagining a neutron star and a black hole as two endpoints of stellar collapse, each shaped by gravity but expressing its power in different ways. Both emerge from the death of massive stars, yet their internal structures and observable behaviors diverge sharply. As you look at them through the calm lens of physics, you realize that violent must be defined carefully. Violence in astrophysics is not emotion or intention. It is energy released, curvature of spacetime, pressure inside matter, and the measurable consequences of these forces. You first consider density. A neutron star compresses matter to nuclear density, roughly 1 trillion kilograms per cubic centimeter. Each neutron sits close to its neighbors, held in place by nuclear forces and the quantum rules that prevent identical particles from occupying the same state. You imagine matter pushed to its limit, resisting further compression with immense pressure. This internal structure responds to disturbances, creating bursts, glitches, and magnetic events. The violence here arises from matter forced into its most compact possible arrangement before collapse becomes unavoidable. A black hole, by contrast, has no internal structure in the observable sense. Its mass compresses into a region bounded by the event horizon. Inside this region, the concept of density becomes difficult to define using ordinary physics. The internal state is hidden. Only mass and spin determine the black hole's external influence. Its violence emerges through the curvature of spacetime rather than through matter itself. Orbiting material accelerates to extreme speeds, and even light cannot escape once inside the horizon. The comparison reveals two very different kinds of extremes, one based on matter under pressure, the other based on geometry under intense curvature. You now reflect on gravity. On the surface of a neutron star, gravity is immense but not infinite. It alters the flow of time, redshifts light, and shapes the behavior of particles in measurable ways. Yet light can still escape. Signals can still reach Earth. In this sense, the neutron star remains part of the visible universe. A black hole, however, represents the limit case of gravitational strength. The event horizon marks a boundary beyond which escape is impossible. Spacetime bends so steeply that all paths lead inward. This is gravity acting with absolute dominance. You explore magnetic fields next. Neutron stars, especially magnetars, hold the strongest known magnetic fields in the universe. These fields fracture crusts, power bursts of X-rays and gamma rays, and channel particles into beams detectable over thousands of light-years. The energy involved in these bursts can exceed the output of entire galaxies for brief periods. This form of violence expresses itself through magnetic stress and sudden rearrangements of field lines, revealing the tension stored within the star's crust and interior. Black holes have no magnetic fields of their own, but the matter spiraling into them generates magnetic structures in surrounding plasma. These structures guide jets that extend across vast distances. The jets do not come from inside the event horizon. They arise from the swirling matter outside, shaped by magnetic fields anchored in the disk. The violence here is not an internal property but the result of spacetime rotation, magnetic forces, and the energy extracted from the accretion flow. The power of these jets demonstrates how efficiently black holes convert gravitational energy into outward radiation. You turn your attention to energy release. When matter falls onto a neutron star, it impacts a solid surface, producing sudden bursts and heat. X-ray binaries containing neutron stars often show bursts caused by thermonuclear reactions on the surface, a consequence of accumulated gas from a companion star. The presence of a surface leads to observable signatures that reveal temperature, composition, and rotation. Black holes, lacking a surface, handle infalling matter differently. As gas approaches the event horizon, it can emit enormous amounts of energy through friction and magnetic interactions in the accretion disk. The efficiency of this process makes black hole disks some of the brightest phenomena in the universe. Yet once matter crosses the horizon, it disappears from observational reach. The violence in this environment is expressed through heat, orbital motion, and jets, not through direct impact. You consider collisions next. When neutron stars collide, they release heavy elements, heat, and gravitational waves. The event is loud in every measurable spectrum, creating kilonovae that glow for days. These collisions reshape the periodic table, producing gold, platinum, and other heavy elements. Their violence is chemical, nuclear, and gravitational at once. Black hole mergers tell a different story. They release no light unless surrounding matter is present. Their collisions emit pure gravitational energy, producing waveforms that sweep through spacetime cleanly and predictably. The violence in these events lies in how spacetime itself oscillates and returns to equilibrium. Despite their immense power, black hole mergers can occur in complete darkness. You reflect on the meaning of motion. Neutron stars rotate rapidly, and their emission beams sweep through space. Their timing reveals stresses, internal structure, and magnetic field evolution. Black holes, especially spinning ones, drag spacetime around with them. This frame dragging creates conditions in which matter orbits differently depending on the direction of rotation. These rotations show how angular momentum expresses itself at extreme scales. You now think quietly about observability. Neutron stars make themselves known through pulses, bursts, thermal radiation, and precise timing. Their violence is visible and measurable. Black holes reveal themselves through indirect signatures, orbital motions, accretion disks, gravitational lensing, and gravitational waves. Their violence is not visible but deeply influential, shaping the motion of matter and light. You begin to sense that the question of which object is more violent does not have a single answer. Each expresses different extremes. Neutron stars push matter to its structural limits, creating magnetic fields, bursts, and instability within solid crusts. Black holes push spacetime to its geometric limits, bending light, stretching time, and merging in ways that release enormous gravitational energy. The comparison becomes a study of different thresholds. The limit of matter versus the limit of gravity. As your thoughts drift through these distinctions, you settle into an understanding rooted in observation. Neutron stars dominate in magnetic violence and internal stress. Black holes dominate in gravitational curvature and energy extraction from infalling matter. Both shape the universe in ways that reveal the boundaries of physics. In the quiet flow of this reflection, you sense how these extremes guide the next step in understanding. The tools needed to observe such environments and the methods scientists use to measure what cannot be seen directly. You begin by imagining the quiet darkness of space where neutron stars and black holes reside, often unnoticed by ordinary light. To reveal them, astronomers rely on tools that can detect signals across the entire electromagnetic spectrum and even beyond it. These tools do not amplify imagination. They measure the real traces left by gravity, heat, particles, and radiation. You settle into an appreciation for how instruments transform the invisible into something that can be analyzed and understood. Your attention first goes to radio telescopes. These instruments detect the rhythmic pulses emitted by spinning neutron stars. Each pulse arrives with remarkable stability, sometimes precise to microseconds. When you listen to the steady pattern through the lens of scientific measurement, you begin to see how timing alone can reveal mass, rotation, orbital motion, and even the structure of spacetime near the pulsar. Arrays such as the Very Large Array and the Meerkat telescope collect these signals by spreading antennas across large distances, increasing sensitivity. The timing variations they capture help map gravitational fields, test theories, and refine models of dense matter. You shift your focus to X-ray observatories. Neutron stars emit X-rays from their surfaces, hotspots, and accretion flows. Instruments like NICER, Chandra, and XMM Newton collect these photons with detectors capable of measuring energy, arrival time, and position. By analyzing their spectra, scientists infer temperature, density, and the strength of gravity at the surface. You imagine these photons traveling from the neutron star, climbing out of its gravitational well, and carrying with them the imprint of redshift. X-ray telescopes detect these imprints clearly, allowing measurements of mass and radius. These measurements, grounded in real data, help constrain the equation of state of dense matter, the fundamental relationship between pressure and density inside the star. You now picture high-energy telescopes observing gamma rays from magnetars and accreting systems. Fermi and Swift detect bursts that last milliseconds to seconds, revealing sudden releases of magnetic stress or interactions in high-speed plasma. These instruments record changes in brightness and timing with precision, giving scientists a window into the dynamics of extreme magnetic fields. The patterns in these emissions are reproducible and consistent with physical models, offering insights into how crusts fracture and how magnetic fields reorganize under intense pressure. Optical and infrared telescopes play their part as well. When neutron stars collide and eject matter, the radioactive decay of heavy elements produces a kilonova glow visible in these wavelengths. Instruments on ground-based observatories detect these signals and analyze their color and brightness. These measurements reveal which elements are present and how fast the ejecta expands. The discovery of the GW 170817 kilonova stands as a clear demonstration of how optical and infrared telescopes contribute to multi-messenger astronomy, confirming heavy element formation in neutron-rich environments. You gently turn your attention to gravitational wave detectors, which have expanded astronomy into an entirely new domain. LIGO and Virgo detect waves through laser interferometry. You imagine two long arms arranged in an L shape, each containing a laser beam bouncing between mirrors. As a gravitational wave passes through Earth, it stretches one arm and compresses the other by an incredibly small amount, far less than the width of an atomic nucleus. The change is minute yet measurable. The resulting pattern shows up as a slight shift in the interference of the laser beams, revealing the passage of a wave generated by distant compact objects. Gravitational wave signals carry information that no electromagnetic observation can provide. They reveal the masses, spins, and orbital dynamics of compact binaries long before any light becomes visible. You sense how powerful this method is. It allows the universe to announce events directly through spacetime itself. The first detections matched theoretical waveforms with astonishing precision, confirming predictions from numerical relativity. This agreement strengthened the confidence that general relativity remains accurate even in the strongest gravitational fields. When gravitational waves and electromagnetic signals appear together, the combined data offers a complete picture. This approach is known as multi-messenger astronomy. GW 170817, the merger of two neutron stars, produced gravitational waves, gamma rays, X-rays, optical light, and radio waves. Each wavelength revealed a different part of the story. The inspiral, the burst, the ejecta, and the expanding shock waves interacting with surrounding material. You let this holistic view settle, appreciating how multiple tools working together can trace the full sequence of a cosmic event. You now explore how gravitational lensing becomes a tool for observing invisible masses. When light from a distant object passes near a compact mass such as a black hole, the gravitational curvature bends that light. Telescopes detect the distorted or magnified images that result. This bending reveals the mass of the object causing it, even if the object emits no light. Lensing offers a way to measure black hole masses in environments where other methods cannot reach. Switching attention to large interferometric arrays, you consider how the Event Horizon Telescope created the first direct image of a black hole's shadow. By linking radio telescopes across the globe, it achieved a resolution equivalent to a telescope the size of Earth. The resulting image of the supermassive black hole in M87 shows a bright ring of emission surrounding a central shadow, shaped by accreting plasma and gravitational lensing. You reflect on this achievement as a demonstration of how technology and theory align to reveal environments once thought unreachable. Next, you follow how particle detectors complement astronomical observations. Cosmic rays originating near black holes and neutron stars arrive at Earth with energies that hint at their sources. Although these particles do not provide direct imaging, their composition and energy distributions help scientists infer how jets accelerate matter. Neutrino detectors also contribute. In rare cases, high-energy neutrinos may come from extreme environments where particles interact at near-light speeds. You now consider how timing plays a crucial role in these observations. Pulsars provide predictable pulses that allow scientists to measure small perturbations caused by orbiting companions or gravitational waves passing between Earth and the pulsar. Arrays like the North American Nanohertz Observatory for Gravitational Waves, NANOGRAV, monitor long-period variations across many pulsars to detect low-frequency gravitational waves. These efforts extend the reach of gravitational wave astronomy into regimes inaccessible to ground-based interferometers. Throughout all these tools, a consistent pattern emerges. Each method gathers measurable signals and translates them into physical understanding. There is no need for speculation or metaphor. The data, arriving as light, timing, or space-time vibrations, becomes a record of real processes shaped by the laws of physics. Scientists refine models through comparison with observation, building a clearer picture with every new measurement. You let your mind settle on the idea that observing the invisible requires not magic but precision. Instruments catch signals that the human senses cannot detect, expanding awareness into regimes where gravity bends light, matter falls at extreme speeds, and space-time itself vibrates. These tools extend human perception into the densest, fastest, and hottest corners of the universe, revealing environments that test the limits of physical law. In this quiet understanding, you begin to sense how these observations, both in light and in gravitational waves, reveal the deeper implications of what compact objects teach about the cosmos. Not only where matter becomes dense or gravity becomes strong, but how these extremes fit into the evolution and structure of the universe itself. You begin by imagining the universe as a collection of structures shaped by gravity, matter, and time. Neutron stars and black holes sit at the most extreme edges of this landscape, acting as natural laboratories where these forces operate at their limits. By observing them carefully, you gain a clearer view of the rules that govern the cosmos. You settle into this idea gently, letting the thought unfold at a steady, calming pace. Your attention first rests on gravity. General relativity has been tested in many environments, but neutron stars and black holes push the theory into regimes where curvature becomes intense and predictions become sharply defined. The bending of light, the timing of pulses, and the detailed shapes of gravitational wave signals all offer ways to check whether the theory remains accurate. So far, every observation aligns with the predictions. You find comfort in this consistency, knowing that even in the strongest fields nature follows a clear framework. But gravity is only part of the story. Neutron stars test the behavior of matter at densities far beyond those found in atomic nuclei. The way a neutron star compresses, cools, and rotates reflects the internal structure of matter under extreme pressure. Observations of pulsar timing, crust fractures, and gravitational wave signatures provide clues about how neutrons interact in these conditions. These interactions cannot be recreated on Earth. Instead, the stars themselves become evidence, offering a rare window into the physics of the strong nuclear force. You now consider how black holes contribute to this understanding. Because they lack a surface, their observable properties depend only on mass and spin. This simplicity makes them valuable tools for testing whether the universe obeys the no-hair theorems predicted by relativity. When black holes merge, the resulting ring-down signal reveals whether the final object behaves exactly as theory predicts. Each detection affirms the relationship between mass, spin, and the geometry of spacetime. Through these signals, black holes become a bridge between theory and experiment. Your thoughts drift toward cosmic evolution. Black holes sit at the centers of most galaxies, including the Milky Way. Their growth influences the formation of stars, the distribution of gas, and the dynamics of galactic structures. When matter falls into a supermassive black hole, it heats and accelerates, releasing energy that can change the surrounding environment. This feedback shapes galaxy evolution across billions of years. By observing the behavior of active galactic nuclei and jets, scientists gain insight into how galaxies grow and regulate themselves. Neutron stars play a quieter but equally important role. Their collisions produce heavy elements that spread through space and become part of later generations of stars and planets. When you think about the composition of Earth, the gold in technology, the iodine in human biology, the thorium in minerals, you are seeing the result of processes that occurred in extreme environments. Observations of kilonovae demonstrate how these elements form and disperse, showing how compact objects contribute to the chemical evolution of the galaxy. Next, you explore how compact object mergers refine measurements of cosmic distance. Gravitational waves provide a way to measure distance directly, without relying on intermediate calibrations. When paired with electromagnetic signals, they create standard sirens that help determine how quickly the universe expands. The rate of this expansion, known as the Hubble constant, remains a central question in cosmology. Mergers between neutron stars and black holes contribute new data that helps narrow the range of possible values. You let this idea settle. Extreme objects quietly guide the understanding of cosmic scale. Your mind moves gently to the structure of spacetime itself. Gravitational waves travel without scattering, maintaining their shape across billions of light years. By detecting them, scientists map the geometry of the universe. They measure not only the strength of gravitational interactions but also how these interactions propagate. This information reveals whether gravity behaves differently at vast distances than it does near compact objects. So far, the observations remain consistent, suggesting a smooth, coherent behavior of physical laws across cosmic scales. You now reflect on how compact objects link the very small to the very large. The behavior of neutrons under pressure determines how large a neutron star can be. That size influences how the star deforms during a merger. The deformation changes the gravitational wave signal, and that signal helps measure the expansion history of the universe. Each step is grounded in observable physics, showing how nuclear forces and cosmological forces intertwine. The universe reveals its connections not through speculation, but through measurable relationships. Your attention shifts to the role of magnetic fields. The strongest magnetic fields known come from magnetars. These fields affect how particles move, how surfaces fracture, and how radiation escapes. When magnetars emit bursts, they offer information about quantum electrodynamics in extreme environments. Observations from X-ray and gamma-ray telescopes capture how matter behaves when electromagnetic forces compete with gravity and nuclear pressure. These bursts become another way the universe exposes its fundamental rules. Black holes also illuminate the behavior of magnetic fields, though indirectly. The jets that emerge from matter spiraling toward a spinning black hole show how energy and angular momentum transfer between plasma and spacetime. These jets extend across enormous distances and can influence the formation of stars in entire galaxies. By observing how they accelerate particles, scientists learn about plasma physics under extreme conditions, confirming theories that describe how magnetic fields organize in high-energy environments. You now think about time. Near neutron stars and black holes, time flows differently than it does at greater distances. These differences affect the arrival times of pulses and the shapes of gravitational wave signals. By measuring them, scientists test how universal the flow of time remains when subjected to extreme curvature. The consistency of these results reinforces the view that time follows the structure laid out by relativity, even under the strongest gravitational conditions. In contemplating these ideas, you sense how compact objects reveal the layered structure of the universe. Each observation tests theories, supports models, or challenges assumptions. The universe uses these extremes to communicate its rules. The behavior of particles, the curvature of spacetime, the distribution of elements, and the expansion of cosmic structure all become clearer through the study of neutron stars and black holes. As your thoughts soften, you recognize that these objects are not isolated curiosities. They sit at the intersection of many scientific questions, linking gravity, matter, light, and cosmic history. Their signals travel across the universe, carrying information about environments otherwise unreachable. Listening to these signals reveals the quiet coherence of physical law, from the smallest nuclei to the largest galactic structures. In this gentle awareness, your understanding turns naturally toward reflection, toward contemplating how these extremes fit into the broader story of the cosmos, and how their quiet persistence shapes the universe's long, unfolding narrative. You begin by letting your mind settle into a quiet space, the kind where thoughts slow and soften. In this stillness, the cosmos feels both vast and steady. The extremes you have explored, the crushing densities of neutron stars, the pure curvature of black holes, the collisions that shake spacetime, start to gather into a single, coherent understanding. You follow these ideas not with urgency but with calm attention, allowing them to unfold at a gentle pace. You reflect first on matter compressed to its limits. A neutron star holds more density than any structure found elsewhere in the universe outside of a black hole. Its crust, its interior, and its steady rotation reveal how matter behaves when pressure forces particles into the smallest space allowed by the laws of physics. Observations of their pulses and bursts show that even under crushing gravity, nature maintains order. Each signal carries the imprint of quantum mechanics, nuclear interactions, and electromagnetic forces. You recognize how these stars serve as guides to the deepest layers of physical law. Then your thoughts drift to black holes, the purest expression of gravitational collapse. They have no surface, no solid crust, no light coming from within. Their influence comes from how they curve the geometry of space and time. You picture an event horizon not as a wall but as a boundary where paths once leading outward now lead inward. This simple change in geometry shapes how matter moves, how light bends, and how time slows. Observations of gravitational waves confirm this behavior with remarkable precision. In this clarity, You feel how black holes turn gravity into a language the universe uses to describe itself. You now revisit collisions and mergers. When neutron stars collide, they form heavy elements and release energy across multiple wavelengths. The signals are complex but measurable, revealing processes that build the periodic table. When black holes merge, the universe communicates through space-time alone, producing clear, smooth waves free from the influence of matter. Each type of collision teaches something different, one about nuclear physics, the other about gravitational geometry. Together, they form a spectrum of extremes, showing the many ways the universe expresses energy. Your attention shifts toward the tools that make these observations possible. Telescopes capture light from across the electromagnetic spectrum, from radio waves to gamma rays. Interferometers detect ripples in spacetime. Timing arrays measure slight variations in pulsar signals. These instruments work independently, yet their findings converge. You reflect on how this convergence strengthens the understanding of cosmic phenomena. It shows that measurements across different domains all support the same physical laws, forming a unified view of the universe. As you let this idea sink in, you notice how consistent the cosmos becomes when seen through these tools. No matter where you look, at a neutron star cooling in X-rays, at a black hole merging in gravitational waves, at a kilonova emitting heavy element signatures, the data aligns with the same principles. Gravity curves spacetime. Matter follows quantum rules. Nuclear forces shape dense interiors. Electromagnetic fields direct particles. Everything acts according to the same set of laws, whether in a quiet stellar remnant or a violently merging pair of compact objects. This consistency offers a calm reassurance. The universe is vast, but its rules do not shift. They remain steady from one corner of existence to another. Neutron stars and black holes simply illuminate these rules by operating at their extremes. You sense how these objects act as boundary markers, showing how far matter and gravity can go before reaching limits. Their existence helps define those limits with clarity grounded in observation. You think about time next. In everyday life, time feels constant, but near compact objects, its flow changes. Pulsar timing and gravitational wave waveforms reveal how strongly gravity influences the passage of time. You picture clocks ticking more slowly near neutron stars and black holes, not through distortion or malfunction, but because spacetime itself stretches. This idea, once abstract, becomes concrete through careful measurement. It reveals a universe where time and space adjust naturally to mass and motion. You now consider distance and scale. Gravitational waves travel across billions of light-years without significant distortion. Light from kilonovae crosses galaxies carrying patterns that reveal heavy element formation. Even when signals weaken, they follow predictable paths set by physical law. This reliability allows scientists to trace events far beyond the reach of human senses. You recognize how compact objects extend your perception, letting you hear and see processes unfolding across unimaginable distances. Your thoughts drift to the connection between the smallest and largest scales. The behavior of neutrons inside a neutron star determines how much the star deforms in the final moments of an inspiral. That deformation shapes the gravitational wave signal. The signal helps measure the expansion rate of the universe. In this sequence, the smallest unit of matter influences the largest cosmic structures. This connection is not metaphorical. It is measured, modeled, and confirmed. You feel how intricately the universe ties its components together. The roles of compact objects in cosmic evolution also unfold gently in your mind. Black holes shape galaxies by regulating star formation through their jets and radiation. Neutron star collisions enrich galaxies with heavy elements, allowing planets and life to arise. These processes occur over billions of years, slow and steady. They show that even the most extreme objects contribute to long-term cosmic growth. Their influence is not destructive alone. It is formative. You reflect on what these objects reveal about human understanding. Much of the universe remains beyond direct reach, yet through careful observation and refinement of theory, clarity emerges. Neutron stars and black holes demonstrate that limits do not equal mysteries. They mark places where known physics stretches to its boundaries, but those boundaries remain continuous with the rules found everywhere else. You sense how the universe reveals itself patiently, one measurement at a time. In the quiet of this realization, you recognize that studying these extremes is not about seeking spectacle. It is about understanding structure. It is about learning how matter behaves when compressed, how gravity behaves when intensified, and how energy moves through the most demanding environments nature provides. Each observation adds a piece to a larger picture that grows smoother and more coherent with every passing decade. You let these thoughts settle into stillness. The extremes of the cosmos, its densest stars, its darkest horizons, its brightest collisions, become part of a calm landscape shaped by physical law. There is no need for exaggeration or drama. The universe is steady, even in its most powerful moments, and it communicates with clarity when given the chance. In this final reflection, your awareness drifts toward the quiet understanding that these objects, in all their intensity, reveal not chaos but order, an order that shapes the stars, the galaxies, and the long unfolding history of the cosmos.